In this video, we are going to be talking about a rule called L'Hopital's rule. L'Hopital's rule is a way to evaluate limits using our knowledge of derivatives. It particularly applies to limits that were in the indeterminate form, which we saw in a previous unit is when you get 0 over 0 or infinity over infinity. If the limit as x approaches c of f of x is equal to 0, and the limit as x approaches c of g of x equals 0, then the limit as x approaches c of f of x over g of x is equal to the limit as x approaches c of f prime of x over g prime of x. And the same idea would apply if the individual limits were positive infinity or negative infinity. So basically, in order to use L'Hopital's rule, we have to ensure that these two pieces are true before we go ahead and actually apply the rule. All right, if we take a look at number 1, okay, we might realize that we can factor it, but basically if we plugged in -2 here, you will see that we will get 0 in the numerator and 0 in the denominator, which means it's in the indeterminate form. So the way that we're going to basically write this is, since the limit as x approaches -2 of x squared plus 5x plus 6 is equal to 0, and the limit as x approaches -2 of x squared minus 4 is equal to 0, we could say L'Hopital's rule applies. Okay, so if we're writing this and we're doing this on a short answer question, let's say you're taking AP Calculus and you need to explain this, you need to show these requirements before you actually do the work. On some of them in this video, we're not going to write it out every single time, but this is the idea that if the limit of the numerator and the limit of the denominator is equal to 0, we can use L'Hopital's rule. So what that basically means is we're going to find the limit as x approaches -2 of 2x plus 5 over 2x. And that we can do because basically we're taking the derivative using power rule of the numerator and denominator, and now we plug in. So I'm going to substitute -2 in for x, and when I do that here on the top, I have -4 plus 5, or 1. The denominator I have -4, so the answer to this problem, number 1, is -1/4. So again, in order to use L'Hopital's rule, we have to show this part here that basically the limit of the numerator and the limit of the denominator gives us 0 over 0 and 0, producing that indeterminate form. Okay, for number 2, the same thing is going to happen. So if I plug 3 in, you can see in the numerator 3 cubed minus 27 is going to give me 0. If I plug it in the denominator, 3 squared plus 3 minus 12 is going to give me 0. So I'm going to say that L'Hopital's rule applies. So this means that the limit as x approaches 3 of 3x squared over 2x plus 1 is equivalent to that original limit. And again, that's because L'Hopital's rule applies. So I just want to clarify once more that anytime we see that the limit of the numerator and the denominator are equal to 0, we are going to go ahead and take the derivative of the numerator and denominator. Again, if you're taking AP Calculus and you're doing a free response question, you're going to need to make sure we write out all of that wording like we did in number 1. For the sake of this video and for making it shorter, we're going to bypass that and we're just going to actually evaluate. So this is equal to 3 times 3 squared over 2 times 3 plus 1 in our numerator here. So basically, this should be a 2, excuse me. So we have 3 squared is 9 times 3 is 27, and that's over 7, and that will be our answer here, 27 over 7. Okay, number 3, when I plug in -4, I am going to, in fact, get 0 for the numerator and 0 for the denominator. So let's use L'Hopital's rule. One thing we want to just think about, by the way, is that the square root of 5 minus x is the same thing as 5 minus x to the 1/2. So we just want to remember that's equivalent, because when I take the derivative using chain rule, I need to be able to see that. Okay, so this is equal to the limit as x approaches -4 of 1/2 times 5 minus x to the -1/2 times -1, because that's the derivative of the inside. The derivative of -3 is 0, so we don't have to do anything with that. And the derivative of x plus 4 is just 1. So let's rewrite this again. Let's clean this up a little bit. So I'm going to get rid of the 1 on the bottom, and I'm going to put this back in the proper format. So I'm going to have a -1 on top, 2 square root of 5 minus x. Basically just cleaning up everything I have on the previous line. Now let's reevaluate. So this is going to give me -1 over 2 times 3, or -1 over 6. Number 4. The limit as x approaches 0 of sine of 5x over x. We'll get 0 over 0, the indeterminate form. So let's take the derivatives of the numerator and denominator. So that would be 5 sine, when I take the derivative here. Okay, number 4, the limit as x approaches 0 of sine of 5x over x. I am going to get 0 over 0, so indeterminate form. So let's rewrite this, but with the derivative of the numerator and denominator. The derivative of sine 5x is cosine 5x times 5. The derivative of x is just 1. Okay, we could rewrite that again as the limit as x approaches 0 of 5 cosine 5x. And now let's substitute 0 in here. So I'm getting 5 cosine of 5 times 0, or 5 times the cosine of 0. Cosine of 0 is 1, so I'm going to get 5 as my answer for number 4. All right, number 5. When I plug infinity in here, this is our first example where we'll get infinity over infinity. That's another variation of the indeterminate form. So I'm going to go ahead and rewrite this with derivatives. So the limit as x approaches infinity of 8x over, when I'm taking the derivative of e to the 4x, I am going to have chain rule, so that's 4 times e to the 4x. Let's say I plug infinity in here, though, and I evaluate. That would give me 8 times infinity, which is infinity, over 4 times e to the 4 times infinity. I'm still getting infinity here. So what that tells us is we have to repeat this process. So I'm going to use L'Hopital's rule again because I got another indeterminate form. So when I do that here, the derivative of 8x is 8. The derivative of 4e to the 4x, again using chain rule, but now I'm going to get 16e to the 4x. Now if I substitute in infinity, I would get 8 over 16e to the 4 times infinity. I have something very small, which is 8 over something gigantic, which is infinity. So our limit here is going to be 0. Okay, so let's just make a note here that we are basically using a double application of L'Hopital's rule. Okay, number 6. When I plug 0 in here, I'm going to get 0 over 0. So let's rewrite this limit. So this is the limit as x approaches 0. The derivative of 2 cosine x is 2 times negative sine x. So I'll write it like this. Over 3x squared. All right, if I substitute 0 in here, I'm going to get negative 2 times sine of 0, which is 0. That whole numerator would be 0. And I get 0 in the denominator. So once again, I'm going to do L'Hopital's rule. It's another double application one. So now I would get negative 2 cosine x over 6x. Now let's substitute in here. So I have negative 2 cosine of 0 over 6 times 0. Negative 2 times the cosine of 0. So that's negative 2 times 1. The denominator is 0. So I'm going to say here that since we get negative 2 over 0, we get something that's undefined. We would basically say that the limit does not exist. Okay, for number 7, the limit as x approaches negative 2 of 2x plus 4 over x plus 2. When I plug negative 2 in there, I'm going to get 0 over 0, so we know L'Hopital's rule applies. So this is equal to the limit as x approaches negative 2. The derivative of the numerator is 2. Derivative of the denominator is 1. And you'll notice that we cannot even plug in or substitute in negative 2 there because we have eliminated all x's. So our answer is just that the limit is 2. And for our last one here, number 8, when we plug in, we are going to get infinity over infinity. So let's take the derivative. We're going to get 14x plus 7 over 18x. But those numbers are still very large. So when I take the derivative, or when I plug in for the limit, I'm going to get infinity over infinity again. So now let's take the derivative. I get 14 over 18, which is 7 over 9, and that's our answer. You might also notice that that's the ratio of the leading coefficients in this problem, and that comes out to be our answer for number 8.